I want you to put yourself right in the middle of the North Sea. The water is this unforgiving gray, the wind is howling, and right in front of you is a colossal structure just sitting on the surface of the ocean.
Right, a truly massive piece of machinery.
Yeah, we are talking about a machine weighing tens of thousands of metric tons.
Yeah.
And it is about to do something that honestly seems physically impossible. It's going to lift an entire oil platform, a steel island, that has been fixed to the seabed for decades, entirely off its base.
And do it all in one single, terrifyingly precise motion.
Exactly.
It is really hard to overstate the sheer scale of what is happening in that exact moment. I mean, you're looking at a load that can weigh anywhere from 10,000 to 25,000 metric tons.
Which is just incomprehensible.
It is. That's the equivalent of lifting several Eiffel Towers all at once.
Yep.
And, this operation is happening in an environment where the water is constantly churning, the vessel itself is shifting, and yet the precision required to pull this off is measured in literal millimeters.
Because if that load shifts unexpectedly, I mean, even just a little bit, you aren't just looking at a dropped object.
No, absolutely not.
You are looking at the catastrophic failure of a rigging system that's holding up the equivalent weight of dozens of jumbo jets.
Right. The stakes are astronomical.
So today, our mission in this deep dive is to deconstruct exactly how this works. We're going to break down one of the heaviest, most sophisticated lifting operations on Earth, using what is called a semi-submersible crane vessel, or SSCV. We're looking at the sources to figure out how engineers basically cheat the physics of the ocean to achieve this millimeter-level precision.
I think the word cheat is highly appropriate here, because the baseline challenge is, frankly, almost absurd.
Right. Imagine trying to thread a needle while you are standing on a moving roller coaster. That is essentially the baseline problem we are exploring today. So, okay, let's unpack this.
Yeah, let's do it.
Before we even get to the lifting mechanisms, we have to establish why picking up a 20,000-ton block of steel at sea is a completely different universe from picking it up on land.
Well, on land, the boundary conditions of your lift are incredibly stable. A crane sits on the solid Earth, and it's utilizing the planet itself as its ultimate counterweight.
Right, the ground does not move.
Exactly. The load does not move until the crane operator decides to move it. The operator controls the hook height, the boom angle, the load position with, relative predictability. But at sea, you lose the Earth.
Yeah, that's a big problem.
A huge problem. The vessel that your crane is mounted on is floating, which exposes it to wave-induced motion in 6 degrees of freedom, and they're all happening simultaneously.
6 degrees. To visualize that for you listening, we're talking about surging forward and backwards, swaying side to side, and heaving up and down. Those are the translations.
Right, the linear movements.
Yeah, and then you have the rotations, right? Rolling side to side, pitching front to back, and yawing around the vertical axis, kind of like a spinning top. The ship is doing all 6 of those things at once, driven by this chaotic wave action.
And the thing is, none of those motions can be fully eliminated in a standard hull. I mean, a crane mounted on a conventional ship in 2-meter waves is not a stable lifting platform.
No, it's a pendulum.
Exactly. It is a highly dynamic pendulum. The hook and any massive load attached to it is moving continuously in 3 dimensions relative to the fixed structure you are trying to lift from.
Which brings us to a, frankly, terrifying phrase that kept popping up in the research. The snap load.
Oh, yeah.
The snap load.
And this is specifically tied to that up and down motion, the heave, right?
Yeah, heave is the ultimate enemy of offshore lifting. Picture the scenario here. You are lifting a 20,000-ton topside off a fixed steel jacket.
The jacket being the structural legs pinned securely to the seabed.
Right, so the platform itself cannot move, but your crane vessel is bobbing in the swells. If your vessel heaves upward by just 1 meter as the lift begins, the massive wire rope connecting your crane to the platform goes completely slack.
Wow. Just 1 meter of swell introduces a literal curve of loose wire into the system. Exactly. And the vessel inevitably has to ride that wave back down into the trough.
Because what goes up must come down.
Right. And that falling momentum is what keeps engineers up at night. The vessel drops into the trough, and that slack wire rope instantly snaps taut.
Oh, man.
The massive platform hasn't moved an inch, but the crane just yanked on it with the entire falling weight of a ship.
So you have just created an impulse force, a snap load, that multiplies the static weight of the platform several times over.
Exactly. Your 20,000-ton platform suddenly exerts the force of 60,000 or even 80,000 tons on the rigging in a fraction of a second.
And nothing can survive that.
No. There is no rigging system manufactured today designed to survive that kind of instantaneous shock. It would tear the crane boom clean off the ship.
That's terrifying.
So you cannot eliminate wave-induced motion entirely because, well, you cannot turn off the ocean. But you absolutely must isolate the crane from that surface chaos.
Enter the semi-submersible crane vessel, the SSCV. When I first look at photos of these engineering marvels in our sources, I was genuinely confused.
They are strange-looking machines.
They don't look like ships at all.
Yeah.
The main working deck sits way up in the air on these massive structural columns, and the actual hull, the part that displaces water and provides buoyancy, is almost totally invisible. It's buried deep underwater.
Yeah, and what's fascinating here is how elegantly this geometry neutralizes wave energy. See, ocean waves are strictly a surface phenomenon. All that violent, chaotic energy decays exponentially the deeper you go into the water column.
It just disappears.
Pretty much. By the time you reach a depth equal to just half the wavelength of a surface wave, the water's kinetic energy has dropped to about 4% of its surface value.
4%, that is a massive reduction. To put that scale into perspective for you, if you are sitting in a two-story house right now, the buoyancy pontoons of an SSCV are sitting deeper underwater than your roof is high.
Right, so the engineers essentially divorce the working area of the ship from the buoyancy area.
Okay, yeah.
A conventional ship floats right at the waterline, absorbing the full impact of every single swell. But an SSCV floats on its submerged pontoons, these giant pressure vessels, sitting 20 to 30 meters below the surface. And the water down there is remarkably still.
I kept trying to picture this while I was reading, and I think I've got a good way to look at it.
Let's hear it.
Imagine you are trying to walk while carrying a completely full, brim-to-brim cup of coffee.
Okay, definitely been there.
Right. A regular ship is like trying to carry that coffee while walking across a trampoline that a bunch of kids are actively jumping on.
Oh, that coffee is going everywhere.
Exactly. But an SSCV is like carrying that same cup of coffee while walking on the solid concrete floor directly beneath the trampoline. The chaos is happening above your foundation, but your feet are steady.
That is a brilliant way to visualize the isolation. Yeah, you are entirely bypassing the zone of significant wave action, and the scale of the machines utilizing this principle is staggering.
Give us some numbers.
Well, take the Hirama Sleipnir, which was commissioned in 2019. It has a single hook lift capacity of 20,000 metric tons. That is the highest ever built.
Wow.
And its predecessor, the Thialf, can lift 14,200 metric tons using its two massive cranes in tandem.
Okay, so the whole design beats the wave action. The trampoline effect is gone. But all this brilliant engineering assumes we can survive the actual moment of the lift. And there's a glaring physics problem here.
There is indeed.
The exact second a 20,000-ton weight transfers from the fixed platform onto the crane's hooks, that vessel should instantly capsize. I mean, adding the weight of a small skyscraper to one side of a floating object is a recipe for sinking.
Oh, it absolutely would capsize, if not for the active ballast system.
Right.
The ballast management is arguably just as critical to a successful operation as the cranes themselves. An SSCV is built with an extensive network of massive tanks distributed throughout those underwater pontoons and the vertical columns.
So by managing the distribution of thousands of tons of seawater across that tank network, the operators basically control the vessel's positioning.
Exactly.
And the terminology here from the sources is important. They mention trim, list, and draft. Just to clarify those for you listening, trim is whether the ship is pitching nose up or nose down. List is whether it's leaning side to side, port, or starboard. And draft is simply how deep the entire vessel sits in the water.
Perfect. So think about the physics of the load transfer. As the immense weight of the platform comes onto the crane hooks, the downward force on the vessel spikes dramatically on that specific side.
The ship naturally wants to plunge deeper,
Yeah.
increasing its draft.
Yes. And having a massive weight hanging hundreds of feet in the air shifts the entire center of gravity drastically upward, which aggressively reduces the ship's stability.
Right, making it top-heavy.
Very top-heavy. So to counteract this destabilization, the vessel must pump seawater out of its ballast tanks at the exact same rate that the weight of the platform comes onto the crane hooks.
Okay, wait, I have to stop you there and try to work out the logic of this. Because the sources mention that this lift process, from the first moment the wires tense up until the platform is fully clear of the base, it could take 30 to 60 minutes.
Yeah, it's a slow, agonizing creep.
Right. A human operator cannot possibly stare at a dial and manually adjust a water pump to match a crane moving millimeter by millimeter. If they're a fraction of a second too slow, the ship leans.
A human operator indeed cannot react fast enough, nor with the granularity required. The margins of error are practically non-existent here.
So what happens if they mess up?
Well, if the deballasting pumps lag, the vessel's draft increases, and it literally begins to sink under the load. Crucially, if the pumps run even slightly too fast, meaning they expel water quicker than the steel weight is transferring, the vessel becomes artificially buoyant.
It starts to rise out of the water.
Exactly.
And if the ship rises weight, the crane wire goes slack.
Yes.
Which brings us right back to that catastrophic snap load we talked about earlier.
Bingo. This is why the ballast is entirely managed by a computerized feedback loop. They have load cells physically built into the crane hooks that are measuring the microscopic stretch in the steel.
So they read the exact tonnage being applied in real time.
Exactly. That data is fed instantly to the central computer, which calculates the exact volumetric equivalent in seawater. It then signals variable frequency drives in the pontoons to spool the massive water pumps up or down in milliseconds.
That is insane.
It relies on a simultaneous stream of data from draft sensors and inclination sensors to maintain a perfectly level deck while thousands of tons of water just rush through the pipes below.
It's basically a 60-minute high-stakes dance of pumping water perfectly in sync with the creaking steel of the crane.
A very stressful dance, yes.
Yeah. Okay, so we have balanced the weight, and we aren't sinking. But we are still floating in an ocean subjected to wind and ocean currents pushing against the broadside of the ship. I mean, you can't just drop an anchor in 3,000 feet of water and expect to maintain millimeter precision. So how does the ship stay perfectly aligned over the target?
You're right. Conventional anchors are entirely useless for this level of precision. This is managed by dynamic positioning, or DP.
DP, right.
The vessel uses a multi-layered sensory approach. We're talking GPS satellites, acoustic transponders dropped on the seabed pinging the hull, and laser reference systems bouncing beams directly off the platform itself.
All working together to continuously calculate the vessel's exact coordinates in space.
Exactly.
And it uses that spatial data to fire its engines, right? But it's not just a single propeller at the back, like a normal boat.
No, not at all. An SSCV is surrounded by azimuth thrusters. These are massive propellers that can rotate a full 360 degrees, distributed all around the perimeter of the underwater hull. The DP system constantly measures the wind speed, the ocean current, the wave drift, and fires these individual thrusters independently to push back against the elements and literally lock the vessel in place.
But the wind and current aren't the only forces the DP system is fighting, are they? Because we have this 20,000-ton steel island hanging off the crane.
Ah, yes, which introduces a massive pendulum effect.
Right.
The DP system isn't just holding a ship in an empty void. It is managing position relative to a fixed platform while simultaneously wrestling with the immense forces of the suspended load. If a sudden gust of wind hits that hanging platform and causes it to swing even a fraction of a degree,
The horizontal tension on the crane wire changes instantly.
Yes.
The load basically becomes a giant bowling ball on a string trying to drag the entire ship sideways.
Precisely. And the DP system must instantly detect that shift in lateral tension and fire the opposite thrusters to counteract it.
It's just a constant battle.
It is. And here's where the engineering gets even more granular. Because even with the submerged pontoons neutralizing 96% of the wave energy and the thrusters fighting the wind, a tiny residual amount of heave still makes it through to the ship's deck.
So it still bobs up and down just a few inches.
Just a little bit, yeah. And we established that even a tiny bit of up and down is deadly for the rigging.
Here's where it gets really interesting. How do they solve that last remaining fraction of movement? Because I was blown away by this when looking at the sources. It's a mechanism called active heave compensation.
It is incredible. It is a system built directly into the massive winches of the crane itself. Utilizing hydraulic or electromechanical power, it continuously measures the vessel's residual vertical motion.
Okay.
It then automatically adjusts the length of the crane wire in real time to cancel that motion out.
And it's exactly like noise-canceling headphones.
It really is.
But instead of a microphone reading incoming sound waves and generating an inverted audio wave to cancel the noise, the ship's sensors read the incoming gravity and ocean swells, and the winch physically reels the thick steel wire in and out to mechanically cancel the movement.
It's brilliant. If the ship heaves up half a meter, the winch instantly pays out half a meter of wire. If the ship drops half a meter, the winch reels in half a meter.
Wow.
The result is that the crane hook and the massive load hanging from it stays at a perfectly constant elevation relative to the seabed. It becomes completely decoupled from the vertical motion of the vessel.
It's literally canceling out the ocean. But, I mean, there have to be physical limits to reeling massive steel cables in and out that fast.
Oh, absolutely. The system has a finite range and speed. It only has a few meters of compensation travel. If the sea state gets too rough, the winch motor simply cannot spool wire fast enough to keep pace with the vessel's violent motion.
So that makes offshore heavy lifts incredibly weather dependent.
Highly dependent. The operational limits, the maximum allowable wave height, are mathematically modeled specifically for every single lift based on the geometry and weight of the load.
Okay, so all this brilliant engineering assumes the 20,000-ton block of steel you are lifting actually wants to cooperate.
Right.
And in a decommissioning operation where you're removing an old platform from the ocean, it absolutely does not cooperate. The object being lifted is a logistical nightmare.
A total mess. We are talking about structures that have been sitting in a highly corrosive saltwater environment for 20 or 30 years.
Yeah, they aren't pristine 3D computer models anymore. The sources detail how these platforms have decades of unrecorded structural modifications. A crew welded a new generator on this side 10 years ago. Someone ripped out a bulkhead over there.
Plus, you have heavy marine growth like barnacles and kelp adding weight.
And all the leftover fluids. The pipes are full of hydrocarbons, chemicals, and produced water. And produced water isn't just seawater, right? It's incredibly dense, mineral-heavy, toxic brine pulled up from the reservoir. That fluid alone can throw the weight off by hundreds of tons.
Easily. And all of those invisible variables create a massive headache for the engineers trying to calculate the center of gravity, or CG. Pinpointing the true center of gravity is the single most critical mathematical variable in the entire preparation phase.
Because if the actual center of gravity deviates from the calculated position, disaster strikes the moment the load clears the base.
Because the load will hang off level.
Exactly.
If it hangs off level, it imposes severely unequal tension on the different legs of the rigging. One steel wire rope might be taking almost no weight, while the rope on the heavier side is stressed beyond its breaking point.
Oh, man.
In severe cases, an off-level load can induce a spin. It starts rotating as it is lifted, generating torsional forces that the crane boom simply cannot withstand.
So they have to painstakingly survey a rusting 30-year-old steel labyrinth to calculate its exact mass distribution before they ever attach the hook.
Right.
And that leads to the actual separation process. Slicing through massive steel legs underwater requires extreme methods.
Very extreme. Teams utilize remotely operated vehicles or deep-sea divers at the connection points. They deploy massive hydraulic shears, abrasive water jets that use ultra-high pressure mixed with garnet sand to erode the steel, or, my personal favorite, carefully placed shaped explosive charges.
But the timing of this cut presents an impossible paradox. I was reading this in the sources and trying to figure out the sequence.
It's tricky.
If you cut the massive steel legs too early, the top side of the platform is completely severed. It becomes a free-floating block of steel sitting loosely on top of the jacket, getting battered by the waves and instantly smashing back into the structure.
And the impact damage to the jacket, which you might need intact, would be immense.
But if you cut it too late, the crane is already pulling up on the hooks while the platform is still physically welded to the base. The crane is basically trying to rip the seabed out of the earth.
Right. You would exceed the load limit instantly.
Wait, so the only way to solve this, you have to basically pull the rubber band tight before you bring the scissors in. You apply the pulling force while it's still attached.
You've hit on the exact solution. If we connect this to the bigger picture, the standard sequence is to apply a highly calculated amount of initial tension, a preload, to the crane hooks before the final cuts are initiated.
Okay, so they bring the rigging completely taut and pull upward just enough to take a significant portion of the weight, stretching the steel ever so slightly.
Yes. Then, and only then, do they make the final cuts with the explosives or the jets. Because the crane is already applying upward force, the very millisecond each steel connection is severed, the remaining weight transfers instantly and cleanly to the hooks. There is no free-floating motion. There is no slack wire. It is a seamless transition from being supported by the seabed to being supported by the crane, connection by connection.
The instant you snip the taut rubber band, the force is already traveling. Okay, so we've cut it. The platform is hanging in the air, the ballast water is pumping, the azimuth thrusters are firing against the current, the winches are humming to cancel the heave. The lift is complete.
Well, not quite. The mission is far from over.
Right, the transport.
The actual lift is really only the midpoint. Once it is hanging freely, the SSCV has to transport this colossal structure to a near-shore location, sometimes 50 miles away, to be set down on a transport barge or a quayside.
And this transit phase imposes entirely different and often more dangerous stresses on the vessel.
Absolutely.
Because transporting a 20,000-ton pendulum over miles of open ocean means the crane boom is taking sustained dynamic fatigue loads for hours on end. The research explicitly notes that the sea state limits the maximum wave heights allowed by the engineers are actually much stricter during the transit phase than they are during the stationary lift.
Yeah, because the hydrodynamic forces acting on the vessel's hull change completely when it is making forward headway through the water.
Oh, sure.
The thrusters are no longer just holding position, they are fighting drag. The structural loads on the deck and the crane hinges are fluctuating constantly as the ship pushes through the swells.
And once they finally reach the nearshore barge, setting the platform down requires perfectly reversing the entire choreography.
Every single step, in reverse.
The ballast system has to pump water in precisely as the load transfers off the hook to keep from bobbing up. The DP system holds the position against the coastal currents. The heave compensation manages the final, gentle kiss of steel to the barge deck.
It's poetry in motion, really.
So what does this all mean? When you see a photograph of an offshore heavy lift, it looks like a crude, simple mechanical action, a big machine lifting a big box. But what you are actually witnessing is a hyper-complex symphony. It is hydrodynamics, material science, and algorithmic computer processing all singing in perfect harmony to temporarily suspend the laws of nature.
I couldn't have said it better. It is the absolute pinnacle of marrying raw, brute industrial power with delicate precision. It requires human ingenuity operating at the very edge of what physical materials can mathematically withstand.
And that leaves me with a final thought I want you, the listener, to ponder as we wrap up. We have talked entirely about the math, the sensors, and the massive steel structures today. But consider the psychological weight resting on the shoulders of the engineers sitting in the control room of that vessel.
Oh man, the stress.
Imagine being the human operator, watching the sensor readouts during the precise moment those explosive underwater cuts are made. You are crossing an absolute point of no return with 20,000 tons of steel hanging in the balance.
Sweating bullet.
Right. The entire operation, the safety of the crew, and a billion-dollar piece of equipment are entirely dependent on your pre-lift center of gravity calculations being flawlessly correct. What must that heavy silence in the control room feel like, waiting to see if your math just successfully threaded a needle on a moving roller coaster?
A very, very profound silence, I would imagine.
Truly. We'll catch you on the next deep dive.